Yeah, I think we can start. Okay, so welcome everybody to our Bangalore probability seminar. So K. Manjunath will give his proofs of KMT theorems.
Okay, so thank you,
over to
Yogesh. Yeah, I'll cut out the video. Just yeah. Okay, so thank you. So it's a pleasure to give the tech talks here as usual. Yeah, it would be better if it was in ISI or IISc or somewhere. But anyway, so sorry. Oh, is it shared or is it not shared? Screen sharing is still paused or?
No, it says you are viewing. Are you? Yeah, I can see
Can
your
you
cursor
see?
moving. Yeah.
You can see
Yeah.
it, right?
Yeah.
Okay.
Yeah.
Okay. Okay. So let me start. So the topic is this KMT strong embedding theorems. Okay, what is it? So let me start with the basic point. So it is about coupling binomial distribution with Gaussian. So as elementary as it gets. Okay. So let Sn be x1 plus x2 plus xn, where xk's are plus minus 1. So for me, I'll just take binomial to mean addition of plus minus 1 most of the lecture. So Sn is a binomial random variable and Z is a standard Gaussian. Then Sn over square root n converges to Z in distribution, that is the central limit theorem. Here is just a different way of phrasing the same thing. CLT is equivalent to the following statement that you can find, you can couple them. Couple means you can construct a probability space on which you have random variables having distribution Sn, let me call it Sn, and a random variable having the standard Gaussian distribution in such a way that Sn over square root n converges to Z almost surely. Or equivalently, Sn minus Z square root n is little of square root n almost surely. Okay, so this is an equivalent statement to CLT. Well, of course, almost sure implies in distribution. The other way is what is called score-hard representation or something. So the one of the main topic of this lectures is a much stronger version of this kind of coupling statement. It is called Tusnady's lemma. What it says is that you have a coupling such that Sn is, so forget the first part, it's there for some reason. So just look at the second part. What it says is that you can couple Sn and Z so that they are within distance Z square plus 11. So this is a far greater improvement over what the CLT is saying. In what way? See, these are two random variables of standard deviation square root of n each. But you're saying that the difference in this coupling is of the order 1 in some sense, because it's not a fixed bounded number. You can't have a bounded, you cannot just have 11 here, because Z is an unbounded random variable. But it is possible to couple such that it is typically of unit distance. And this is what Tusnady's lemma is. So this is a very strong, so from square root 10, you have gone up to, in some sense, order 1 in probability. Okay, so Tusnady's original version had better constants. And you can say for all n greater than equal to 1, blah, 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 with some constants. Here you have maybe a half Z square. Instead of 3, you may have 1. You may, instead of 11, you may have 5, something like that. Most of that does not matter. Okay, for most purposes, it doesn't matter. I don't know if it matters anywhere too much. It's good to have decent constants, and this is the way we are going to see it. But what is important here is this power of 2 here of Z is very important, because Z, Y, it will show up, but it is kind of seen here. So probability that Sn minus Z root n deviates by something as large as X decays exponentially. That is because Z is Gaussian, Z square still has a moment generating function. Therefore, it has exponential decay, and that is why that power 2 is important. If you had power 3, it would be worse. 4, etc., it would be worse. Now, this is a very nice one, naturally motivated by this, but it is also the main reason for this is that is the key ingredient in the
Manju,
yes.
Matthew has a question.
Yes.
Z
Yes.
changes with n?
No. Okay. Yeah, I mean, yes, so that's a good question. You can have a single Z here. Yes, you can have a single Z here. Okay. Yeah, I mean, actually, that's a good point. Actually, there are things like that also. But I'm just saying that, yeah, you may take it Zn square root n also. I mean, for the purposes of this talk, actually, it is true that the difference is there in a different sense. Later, I will say. So, and actually, yeah, but yeah, for this purpose, you can even assume this is Z, not Zn. Okay, that's also okay. Yeah, yeah, okay. So let me proceed. So this is actually a key ingredient in the proof of the KMT theorems. So actually the statement here is for fixed n. So that's why I have not written Z. I mean, if you are asking for the entire sequence, this is for fixed n actually. So this is, by the way, this is not saying that for all n. This is for a fixed n, you have a coupling of Sn with a Gaussian. So you can call it Z or Zn. Yeah. So what happens? So this is the question. What is this KMT theorem? So I will say that. So KMT stands for Komlós-Major-Tusnády. So that is a coupling like that, but for random walk with Brownian motion. Now let's take S is S0, S1 dot 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 is simple random walk, symmetric simple random walk, and W is, let us say, standard Brownian motion in one dimension. Then Donskoy's theorem, which says that after scaling the simple this SSRW converges to standard Brownian motion, that can also be interpreted in equivalent way as a coupling of the random walk with Brownian motion in such a way that if you look at the maximum up to time n of the random walk with the Brownian motion, that is little o of square root n almost surely. Actually, here Matthew's question makes sense. So this, we are looking at the maximum up to time n. Do you use the same Brownian motion or do you use different Brownian motion? Is it W super n sub k? What I mean here is that W may depend on n. For fixed n, there is a Brownian motion W such that this is small. Okay. So whereas there are theorems which also consider a single Brownian motion, but this fine point can be ignored here. So the point is that you can couple a random walk. So this is just Donskoy's theorem that you can couple a random walk up to time n with a Brownian motion up to time n, so that the distance is smaller order than square root n. However, what KMT theorem says is a much stronger statement that you can couple them so that the maximum distance up to time n is really of the order of log n. Okay, so that is a very strong statement. I mean, big improvement from square root n to log n. And this log n is optimal. The precise statement is that this maximum can be coupled so that it is less than this c times log n plus x with probability at least 1 minus e power minus x. Okay, so it's in that sense. There is a constancy such that this happens for all n. So as I said, it is improves upon square root n to all the way to log n. It is not big O of n. In the univariate case, we came from square root n to all the way to really unit order. Here you cannot do that. When you consider paths, the entire paths, and you're looking at the worst case deviation over the whole path, the endpoint deviation is what we considered earlier, but the worst case is going to be large. That will be log n, and that is known to be optimal. And this is just, I have stated it for simple symmetric random walk, but Komlós-Major-Tusnády, they showed it for exercise with exponential tail. I did not write the years here. This is in 1975 approximately. So this paper of this is a very important result in probability. One can say it's a fundamental result. It compares very fundamental objects we care about, random walk and Brownian motion, and it is asking for the best coupling. And there is another KMT theorem, which also let me mention here. So which is for empirical processes. Okay, so this is of more importance in statistics. So what is that doing? What is that? So let us take v1, v2 dot 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 i.i.d. uniform random variables, uniform on 0 to 1. Then you look at the empirical spectral distribution, empirical distribution function, fn of t, which is the proportion of k for which vk is less than equal to t. So it's just the distribution function of the empirical distribution. And then the empirical process is, so the true distribution is t. So you take the difference between fn of t and then scale up by square root of n. That is what is called the empirical process. Okay. So, or more precisely, the uniform empirical process. So this is a function, random function on 0 to 1. And this is used, we see these things in statistics in the Kolmogorov-Smirnov test and so on. So you study how big this is to see whether the sample is really from uniform or not. Okay, so Kolmogov and Smirnov worked out the test. Basically, what they found was the maximum of this. They found the limiting distribution. Maximum of Gn, they found the limiting distribution. But later, after Dansker, one sees that as the maximum of just a Brownian bridge. That limiting distribution was just the maximum of Brownian bridge, which is defined like this. If W is standard Brownian motion, then you Wt minus Tw. And this is just Brownian motion on 0, 1, conditioned to be back at the origin at time 1. So what is the Dansker theorem telling you here, which is far bigger improvement of Kolmogov-Smirnov, is that if you look at this Gn, well, I have further scaled it by square root n to make it look similar to the previous situation here in the Dansker case. So, so you multiply this Gn minus W bar. So you can couple empirical process with Brownian bridge such that the difference is like little of 1. I mean, it converges, or if you multiply by square root 10 here, then it is little of square root 10. And what is the corresponding improvement of Komlós-Major-Tusnády? That you can bring this down all the way to log n. Okay, so this square root 10 mod Gn. So in other words, the difference between Gn and W bar, you can couple them so that the difference is like log n over square root 10. So again, it's very much like this one with random walks. This is for empirical process. They are very similar theorems. One can prove them in similar ways. Yeah, if there are any questions, please interrupt. So these are the statement of the main theorems. So let me just recap. I mean, so I'm no expert in this area. So I'm just, I don't know all the kinds of proofs that are there. There are two proof strategies I am aware of. Okay, we will develop on both of them. One is, I just call them combinatorial and analytic. I couldn't think of better words for them. So the combinatorial proof, this is sort of the original proof of Komlós-Major-Tusnády, and there are many, many developments. So then there's paper of Massat, which is very nice. Then Carter and Pollard. So I would refer people to this very nice book of Pollard called User's Guide to Measure Theoretic Probability. It has a very good exposition of this, and so there is a proof of that. And then there is another proof, second proof strategy. This is due to Chatterjee from around 2008, and that is by and large, it is called, you can call it Stein's method. Roughly speaking, that is Stein's method. He did it for a simple symmetric random walk, and it was extended to some larger class of things by Bhattacharjee and Goldstein. Okay, let me outline what is the kind of proof. I mean, it's a very broad outline of the proof. These proofs have two parts. Okay, one is the univariate coupling. So these are about coupling paths, right? I mean, in function space, we're working in function space and you're looking at maximum difference between two paths. One is Brownian motion or Brownian bridge, and other is your random walk or empirical process. But it starts with a univariate coupling, such as Tusnady's lemma that I had in the first one, comparing binomial to Gaussian. So this is actually a key part. I mean, I would say this is maybe the more crucial part. So Tusnady's lemma or other similar coupling lemmas. And so in the combinator, so both proof strategies have these two parts, the univariate part and the univariate to paths part. So in the univariate part, in the combinatorial one, you use Tusnady's lemma. So Chatterjee uses some other lemmas which are of a similar nature. I will state them later. So there are some similar coupling lemmas. In the second lecture, I will mention them. I have no need to say, but they are of a similar nature, let's say. So what does in the combinatorial proof, what you do is you can think of this as the basic de Moivre-Laplace limit theorem. We show in first probability lecture class that binomial converges to Gaussian. How do you do that? You take the binomial mass function and use Stirling's formula to show convergence to Gaussian. It is a much more involved version of the same thing, actually. You have to use Stirling's formula to higher order of asymptotic expansion, but there are much more involved. Even this very nice presentation in Pollard, it takes 10-15 pages to write down these things, actually. So the combinatorial proof really is this one. Analytic proof, that is where Chatterjee uses the Stein's method method, okay? And then that is for the univariate part. But then there is a step going from univariate to the paths coupling. That is, there are two steps. There are two ways. Again, in the two proofs, there are two different ways. So in the standard one, there is what I just write it as dyadic approach. I am not actually going to explain this step much in this talk. It will not feature much in this talk. These are understood now. So one is the dyadic approach. What you do is, so here I have written for the empirical process. See, empirical process and the Brownian bridge both are zero at the endpoints. So you first couple them at half. So Gn at half at Brownian bridge at time half. That way you couple them is using the univariate coupling lemmas. Once you couple them, then you condition on that, and then you then couple at the next dyadic points, 1/4 and 3/4. At 1/4 you couple them, and then at 3/4, and so on. You have to go to a certain number of generations, which is about basically a multiple of log n number of generations. And then you have to analyze how much error you have occurred in all these steps, and that is the very broad outline. It's not complicated actually. It's nice, it's very nice, but not complicated. So what Chatterjee does is a slightly different one. He avoids this dyadic approach. He does a very cunning induction, actually. It is a very, induction. I say cunning because you have to frame the statement properly. You know, induction statements, a stronger statement may be more easy to prove because the hypothesis is also the conclusion. So what Chatterjee does is an induction on n. I won't say anything more here. Maybe in a second lecture, I may say what is the induction statement. Okay, so this is the broad outline of the two proof strategies I'm aware of. So what is the subject of this talk? We are going to, there is one idea basically, and we try to simplify both these. Okay, and when I say simplify, it's really concentrating on the first step of univariate coupling lemmas, not really. I have very little to add or nothing to add to the going from univariate to coupling to paths. It is really these univariate coupling lemmas that we try to improve on both methods. And yeah, so you can see whether it is simplification or not, you can see. So in the first talk, in the rest of this first talk, I will talk about the how to use our idea to simplify the combinatorial proof, namely the Tusnady's lemma, how to get a proof of that. In the second lecture, I will do the same for the univariate coupling lemmas in Chatterjee's method. Okay, so what is the idea? The basic idea is something we learn in first real analysis class. You use Cauchy criterion. Okay, it's hardly a new idea. So this, so in real numbers, if you want to show xn converges to x, you can do things like this. You can show xn and xn plus 1 are less than 1 by n square, or xn and x2n you can compare. And let's say you prove it is less than 1 over n to the epsilon. Either of these statements will suffice to prove xn goes to x. In fact, you get quantitatively because you can sum this from xn, xj plus 1, you can sum over j greater than equal to n. And so the sum of 1 over j square will give you something like 1 by n. You get a quantitative bound like this. Or if you use this xn and x2n comparison, you can compare xn and x2n, x2n and x4n, x4n and x8n, and so on, sum that difference. And you get that the difference is like 1 over n to the epsilon because times a geometric series, which is some finite number. So this is basically the idea that in this Tusnadi lemma and so on, what we are trying is to compare binomial with a Gaussian. Instead, you compare binomial with binomial. This is really the main idea, okay? So why? So in some sense, okay, binomial converges to Gaussian, but still binomial is a different kind of object than a Gaussian. Okay, so whereas binomials are similar to each other, they are both combinatorial. So Gaussian is a, so to speak, a continuous distribution, and Sn binomial is a discrete thing. So whereas when we compare binomial with binomial, you can hope for a purely combinatorial proof because everything is finitary, right? So that is what we do. So the idea that you can use Cauchy sequence is fine, but why it is recommended here is that you are comparing like with like rather than like with unlike. So that is what we do. This talk, we take binomial, we compare. So instead of comparing Sn to Z root n, we compare 2Sn to S4n. Why 2Sn and S4n? They have the same mean and variance, just like Sn and Z root n. 2Sn and S4n both have the same mean and variance. That's what need to be coupled. So what we do is in the first lecture, we do this. by combinatorial method, so to speak. In the second method, by coupling finite Markov chains. Okay, so that is the whole of it. So now I start the main part of the first lecture. Any questions or anything, please interrupt. So what I will do now is I want to prove this type of Tusnady's lemma by this idea of just comparing binomials with binomials. Okay. So this is our version of the combinatorial proof. So instead of Tusnady lemma, we have this lemma, which is exactly doing this point that we compare 2Sn with S4n. So you may remember, okay, so let me just quickly show again. Tusnady's lemma, you had Sn and Z root n, and mod Sn is less than mod Z root n plus some constant, and Sn and Z root n differ by Z square plus 11, something like that. So what here we have is 2Sn and S4n are compared, and there is an entirely analogous lemma. So S4n is to be thought of as like Z root n or Z square root 4n, and 2Sn is smaller than mod S4n. Again, this statement may not be clear why we need. Let's leave that. So it is this one that shows the distance between the two can be made small. 2Sn and S4n are random variables of standard deviation square root n, but they differ of unit order because this thing is of unit order, right? S4n square is of order n, so it's of unit order. So here I quickly indicate the idea. I mean, what I just explained in a moment ago, that Cauchy, from Cauchy sequence, you can go to the sequence, I mean, to the limit, right? So how do you go from this to the actual Tusnady lemma? It's actually simple. You just, so I won't do this in the second lecture, but here just let me indicate once. So you just, you start with some n. So this is, by the way, I have stated it for only even numbers n. For odd numbers, it's just a slight modification of it, no big deal. So let's fix an even number n. N is fixed. And then what you do is you look at Sn by square root n, S4n by square root 4n, and then you go in multiples of 4, S4 to the kn over square root 4 to the kn. This is converging to Gaussian, right? So what this lemma, this Tusnady type lemma tells you is a way of coupling Zk with Zk plus 1 for every k. Okay, so this coupling, if you just scale it by blah, 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 you will see that it can be stated that Zk and Zk plus 1 can be coupled to satisfy these two statements. Okay, I am not able to highlight that. Okay, so these two statements, that mod Zk is less than equal to Zk plus 1 plus 2 over this square root 10, 2 to the k square root 10, and Zk plus 1 differ by something like 1 by square root 10. Okay, it's just a scaled version of this. But once you have this, you see, look at the second statement. What is the difference between mod Zk plus 1 and Zk? It is Zk plus 1 square over square root 10, and there is a 1 by 2 to the k. And by Bernstein or Hofding inequalities, we know Zk is not going to be very big. It's like you have tail probabilities for Zk's. So it's smaller than, let's say, 2 to the k over. It is a very generous bound for mod Zk. With high probability, it is that small. But once you have that, what this shows is Zk is actually a Cauchy sequence, almost surely, because this is small, some 2 to the, excuse me. Yeah, so this is, Zk is a small exponential, but you have a 2 to the k here. So the whole thing is summable in k. And you say that Zk is Cauchy. So it will converge to some Z, which has to be a Gaussian random variable. What else can it be? It converges almost surely. And this inequalities go through to the limit. You just let the right side go to the k go to infinity, you get mod Zk less than mod Z plus 2 over square root 10. You just sum this these two inequalities. Then mod Zk minus Z will be less than something like this, which is actually Tusnady's lemma. Just in this, you just multiply by square root 10. If you multiply by square root 10 Zk is Sn, and square root 10 Z is the other thing. So Zk square root 10 is Sn. Sn minus Z root 10 is smaller than Z square plus 9. That's what you get. So this is just a point that Cauchy, doing this Cauchy business is enough. But why is it that we can do it? That is the key part of it. So how can we prove a lemma like this? How can we couple Sn and S4n? By what method do we do that? Okay. Now, a very general fact, trivial almost. So to couple two integer valued random variables, you just have to have an inequality of tails like this. Suppose x and y are two integer z plus valued random variables, suppose. Then suppose you have this type of inequality between tails. That means you want to bound probability tail of y, that is probability that y is less than equal to greater than equal to k. You may not be able to bound by probability x greater than equal to k, but you have to go a little to the left to be able to achieve that. Let's say probability x greater than equal to k minus f of k beats this, where f of k is some function. And similarly, to bound the tail of x by the tail of y, you have to go a bit before k. Instead of k, you have to go as far as k minus g of k. In such a situation, you can couple x and y so that x is at least y minus f of y and y is at least x minus g of x, all simultaneously. You can do this. This is actually a trivial statement. If you want, you can utter words like Hall's marriage here, but no need. You can just see the natural way in which you generate discrete valued random variables. You take a uniform and you break the interval 0, 1 into intervals which have the probabilities at 0, 1, 2, 3, 4, etc. And then you assign, that's how you generate x and y as functions of uniforms. So that natural coupling using one uniform random variable will just do this. Okay, so there's no need to explain this one. So point is that we have to compare the tails of the random variables that we are interested in. In our case, it is 2Sn with S4n, where n is an even number. Okay. By the way, am I audible or is it Yogesh?
Yes.
You are audible.
Okay, because there is a lot of noise here due to rain. I
Oh.
cannot hear what I am saying.
No, we are able to hear. At least I'm able to hear clearly.
Okay, fine. Yeah, but you have to speak loudly to interrupt me. Okay, because
Okay.
I just cannot hear. There is a lot of rain here. So let us look at so 2Sn and S4n, and we have to couple them. So we introduce the mass functions. Actually, slight difference. So let's introduce this notation. Alpha m of k is the mass function of, basically these are the mass function of S2m by 2 is x and y is S8m by 4. Well, you have to compare, you just divide both of these by 2, but that's all I'm doing. S4n by 4, that is S8m by 4, and S2m by 2, here I have taken. So what we have here is the mass function of S2m by 2, that is alpha m of k. And the beta m of k is the mass function of the integer, the ceiling of S8m by 4. Okay, you can couple the well, the ceiling is no big deal. It makes a difference of at most 1. So you can couple S8m by 4 with the integer part by a distance of 1. So it's enough to couple x and y, which have these mass functions. The reason I just divided by 2 is then it has no gaps. S2m has gaps of 1, right? So I just divided by 2. So that is the reason I did that. Okay. So what we need is the tails of these mass functions. Alpha m bar of k is the tail of this alpha. I should write here subscript alpha, it should be alpha m of j. And beta m bar of k is the tail of beta m. So according to this lemma, what we need to do is to compare these things. So for example, this statement is what we want to prove. Why? If you do this, suppose alpha m bar of k is less than equal to beta m bar of k, that means an inequality like this is satisfied here with g of k equal to 0, because alpha m bar of k is less than equal to beta m bar of k. You don't even need to go a little to the left to get that comparison. Whereas, so the other side, you will need a comparison that the tail of alpha m, you have
It's 3 o'clock.
So on the other side, we have to go a little to the left. So if you want to take the tail of this beta distribution at L, then we have to go a little to the left. How far? L minus L squared over M. This is the quadratic in the Tusnadi, basically. Okay, so that's what comes here. So this is the kind of statement that we really need to show. Okay, so something about the tails of these distributions, mass functions of S 2m by 2 and S8m by 4. So, so because once you do this, g of k will be 0 and f of L will be L squared over 2m plus 1. And that immediately gives you the coupling, which is this. On one side, so one side you should get 0. And but as you say here, this is only for even numbers. And also there is an integer part, so you just get an extra constant, additive constant, there will be an extra bit plus 2 here. The other way is precisely this L squared by 2m will give rise to this thing that you can couple them so that, because you see the coupling lemma says you have this f of y and g of x. That's the extra bit. Y less than equal to so this extra bit is exactly this s squared over 8n. Okay, so that's what you have to show. So in short, this is what we have reduced our Tusnadi lemma to. Okay, and then question is, how do we show this sort of thing? So this was just generalities about how to couple. You have to just compare the tails, and I have written down.
Manju,
Yes.
one question.
Yes.
You said the constants are not relevant.
Yeah.
Okay, but still, nevertheless, I want to just ask that the constants you get, how do they compare with the original ones in Tusnadi?
They are decent. Actually, the constants we get are very good. They are not optimal. Actually, Tusnadi's original lemma has the best constants probably. Or maybe it was improved later, I'm not sure. But many of the later proofs have even worse constants. Our constants are decent. I mean, so this, well, what is it? Here it may be instead of 2, it may be 1. Instead of 9, it may be 1. I mean, max. I don't think it is 1, it may be 2, something like that. So these are actually pretty decent. The one thing is here, Tusnadi has a factor of 4.5 on this. But we don't get that half. We get we can get 0.3, but we can't get half. Sorry, he has 1/4. Where he has 1/4, I can get something like 0.3. But I didn't worry too much about that after a while. Okay.
Yeah, thanks.
Okay. So, so by this generality, we have reduced it to the comparison of these tails. Now, how do we handle the tails of binomials? Okay. So here is something. So that let's write down. So these are binomial, right? So the binomial mass function, I wrote here that alpha m is the mass function here. But we can write explicit binomial formulas for that. It is alpha m of k is in fact this binomial coefficient 2m choose m plus k over 2 to the 2m. And beta m of k is the mass function at 2 points added, but that is another binomial, something like 8m plus 1 choose 4m plus 2k or 2. Exact form not relevant, but these are explicit binomial coefficients. However, the tail will not have an explicit formula. The tail of binomial does not have explicit formula. It is a difficulty one often has to contend with, but it does have estimates. This is the kind of thing, any information theory course, you will see this kind of estimate. For binomial coefficient itself, there are these types of estimates. And for the tail of the binomial coefficient also, you have estimates like this in terms of the entropy function, e to the minus n times d of k over n. Okay, so where d is the basically the entropy function with respect to Bernoulli half distribution. So these are standard estimates that are very much used and taught in any information theory course will have this kind of estimates. They are used a lot. But so will this suffice? No, this won't suffice. This will only suffice because you see the tail, when you look at the second estimate in the tail, one side you have e to the minus n d of k over n, where d is this entropy of k over n with respect to half. On the left side, you have something with an extra bit. So these right side and left side differ by a huge factor. Well, huge in the sense, for many things it doesn't matter, but it does matter. Root n over square root of k into n minus k is not same as 1. Okay, so there is a big, and anyway, there is a constant. So this won't suffice. This is not fine enough for our purpose. But for far enough in the tail, if you take k like half n and so on, then this is very good. These estimates are sufficient. So if you want to prove these types of inequalities that we are trying to do, what I have written here is to show. Okay, I don't know why it doesn't select this kind of stuff. So the thing that I'm trying to show here in the alpha m bar of k less than equal to beta m bar of k, the tail estimates that I want to show, you will only get it in the far tail by using these things. You won't get it for every k. Okay. So how do you do it for small k? That is the crucial part. Now what I will do is I will not actually tie together all the threads. I will show you how it is done for small one. Instead of comparing the tails, I will show you how to compare the mass functions themselves. Okay. So this is exactly a similar looking statement, except that I have removed the overline, which means that we are not comparing the tail, but we are comparing the mass functions. Now that won't suffice. What you have to, what the actual proof, I have written it in details in the paper, is that this won't suffice. You have to combine it together with these types of estimates for the binomial coefficients. And bootstrap into 3 steps to go all the way from small k to big K. Okay, so that step I won't show here. I mean, it's not, I think, informative in the talk. What I wanted to emphasize was this point that the claim that this can be compared using some combinatorial methods. So I will just show you how this key combinatorial lemma is proved. If I don't worry about the tails of the distributions, but just look at the mass function of 2Sn and S4n, or these are Sn by 2 and S4n by 4, something like that, then this inequalities hold. Okay, these statements are exactly the analog of the other one for the tail, except you may see one small difference here. This is instead of L square by m, I have L cube over m squared. Actually, this is a good feature. In fact, I thought I had discovered something new, but actually this is actually the best form of Tusnady's lemma. So Yogesh, you asked about constants, but there is a more further improvement due to Carter and Pollard, where in Tusnady's lemma, instead of z square on the right side, they had z cube over n. By and large, it doesn't make much of a difference. I mean, in the worst case, it makes no difference, because when z is of order n, this is same as z square. But in typical situations, z cube over n is better than z square. So this combinatorial lemma strongly suggests that we should also be able to, the Carter-Pollard improvement in fact falls out of this method without looking for it. I mean, this just came out. However, let me say that we haven't actually worked it out, because as I said, this lemma is not enough. We have to combine it with these estimates to go all the way. So in the end, in my version of Tusnady's lemma, we only have square, but it should be possible to get something like S4n cubed over n to the 3/2 type thing. But okay, I don't do that. Sorry, S4n cubed by n square or something like that. So, but anyway, so let's talk about this combinatorial proof of this one. Any questions, or if I go fast, or I mean, if things are not clear what I'm doing, please interrupt me. I'll be happy to explain. So the rest of this talk, so the second talk is more or less disjoint from this, in the sense I will just recall the motivation and then show the other method. But in the rest of this talk, I want to show you combinatorially how one gets these two things. Okay. This is, in my opinion, somewhat simpler than the usual, but maybe only at an expository level it's possible. Okay. So this is what we are setting out to prove. How do we prove something like this? This alpha m, let's recall, alpha m is the mass function of S2m by 2, and beta m is kind of the integer part of S4n by 4 or something like that. So what we have to show is these two. These are color coded. The brown part here, alpha m of k less than equal to beta m of k, is basically showing that you define f of mk, which is the ratio of beta m over alpha m. You are supposed to show this is greater than equal to 1, right? So this is what this is claiming. You want to show this is greater than equal to 1. But that is this exact combinatorial expression, ratio of two binomial coefficients. And the other side is similar. This is supposed to hold for all k, the first one. The blue one is supposed to hold for k and l satisfying this relation. K is sufficiently small compared to l. So the point I didn't emphasize here, when L is small, this is very close to L. But when L is very large, L is comparable to M, then you have to go sufficiently below. Okay, that is necessary. Because even the supports are different actually. Yeah, I didn't say that S2n support and S4n, 2S2n support and S4n support are actually different. So you cannot expect without some corrections like this. You have to go far at the tail, one side of the tail. So you are supposed to show this. So if H is, so I define here beta m of k over alpha m of k minus h, where h we are going to take to be of this order, this L cube over 4m square plus 1 type thing. And then you have to show that gh of mk will be less than equal to 1. Okay, so that is the first statement here, the brown one, is just that f of mk greater than equal to 1. The second statement is gh of mk is less than equal to 1 if h is sufficiently, if k is sufficiently, I mean, yeah, what have I written? H plus 1, yeah, if h is sufficiently large. If this h 4h minus 1 m squared to the 1/3 beats k. That is just the rewriting of this statement. Now here is where I asked here, I wrote here bijective proof. Unfortunately, I say combinatorial, but I don't have bijective proofs of this. Just look at this f of mk if greater than equal to 1. Both the numerator and denominator of f of mk have obvious counting interpretations. So can one get some simple bijective proof of this? I don't know. Yeah, so maybe people who count in life like Arvind, yeah, so they can think of such things, but I can't. I couldn't think of a bijective proof, but nevertheless, we have a proof. And a similar question here, but I don't see how bijective proof will throw up this condition L cube over m square plus 1. But anyway, so the way we do it is slightly different. I don't see how to compare this 8m plus 1 choose 4m plus 2k with this other binomial directly. What we do is in 3 steps. So both these proofs are actually very similar to each other. So let me, although the second one is the more interesting because then you ask where does this m to the 2/3 etc. come. But it's just easier. So I will show the proof of this brown part and then later in the end I indicate how the other one is shown. So you have to show f of mk greater than equal to 1 for all m and k, right? So let's take k equal to 1. F of m1 greater than equal to 1. That follows from the second and third statement here. See, f of m1 converges to 1, I claim, and f of m is actually 1 is decreasing in m. So if you have a decreasing sequence converging to 1, it was always greater than equal to 1. So that second and third statement here will show that f of m1 is greater than equal to 1. The first statement says that f of m2 is greater than equal to f of m1. Therefore, that's also greater than equal to 1. And f of m3 is greater than equal to f of m2. So that's also greater than equal to 1 and so on. So it's kind of easy to see that these 3 statements imply that f of mk greater than equal to 1 for all k. Okay. So the point is to prove these 3 statements. Now, the last statement is trivial. So let me indicate. So f of m1 goes to 1 is simple. It's just Stirling formula. Here you know f of m1. What is f of m1? Okay, I don't know why I have written it. Yeah, f of m1 is written here. You just apply Stirling's formula to that, or you can say local CLT. We know that f of m1 will go to 1. Okay. So the other 2 steps are slightly more interesting. How do I show f of m1 is decreasing in m? Okay. So that is what is done here. F of m1 greater than equal to f of m plus 1, 1. For that, you can take ratios. So if you take ratios of 2 such things, all the binomial, most of the factorials will cancel. Okay. I don't want to inflict on you the details of this calculation, but there is a small interesting point. I think some people may find it interesting how it comes out. So when I look at the f of m plus 1, 1 to f of m1 ratio, I get some expression. You can see, f of m plus 1 will have an 8m plus 9 factorial. Divided by 8m plus 1 factorial will give you some factor like 8m plus 2 to 8m plus 9. Similarly, there are many other terms. Okay. So you write this entire expression out. There are, I don't know, 10, 11 terms in the numerator and so many in the denominator. There is a little bit of cancellation and you can write it as a ratio of px over qx, where I have just written x is 8m for simplicity. So it's a polynomial. You can write this as 8m and 8m plus, so you just multiply by factors of 8 and you can write everything in terms of 8m. So it is a polynomial in 8m and polynomial in 8m in the denominator. So it's a ratio of 2 polynomials of x. The polynomials explicitly turn out to be this: x plus 16, x plus 9, x plus 7, x plus 5, x plus 3, and the other one is this. What I did was I just plugged it on Mathematica and I could see that px is less than equal to qx. I mean, you just subtract px from qx, you can do. But here is a nice way, and it turns out to be nice. You don't need to do it numerically, because this vector 16, 9, these are the roots of this polynomial, so to speak, or the negatives of them. 16, 9, 7, 5, 3. That vector majorizes 12, 10, 8, 6, 4. This other vector, the zeros of this. So what that majorization means, I have explained here. It means that the partial sums of the first one beat the partial sums of the second one till the end where they become equal. 16 beats 12, 16 plus 9 beats 12 plus 10 and so on. In the end, the total sum is 40 in both actually. So, and there is something called Shrew concavity, which says that this px, this polynomial in x is actually for positive x, it's Shrew concave in these roots. So that implies this inequality that px is less than equal to qx. Okay, if you don't want all these tricks, you can just do it in Mathematica and you will see that the difference qx minus px is a polynomial which is seen to be positive. So this is how you do the this one. And for the other part also it is similar, less interesting. So the first part, how do I show that f of m for fixed m, it is kind of increasing in k. So again, you take ratios to cancel most of the terms. It's even simpler because when you take ratios for fixed m and different k, lot of even more factorials cancel, and you get a ratio which is some, again, ratio of two polynomials like this. And you can see that the difference of the two is actually non-negative. Okay, so this is the proof of the three inequalities here, and you show f of mk greater than or equal to 1. And consequently, you have shown this type of comparison between the mass functions. For the second part, the proof is more or less identical. So except that when you do this part, f of here, gh of mk plus 1 and gh of mk, you do the ratio. Then this condition, so you get a ratio of two polynomials like this, but when you take the difference, we don't get a positive polynomial, we get a polynomial like this, where x is 4m and a is 2k. Okay, x is 4m, a is 2k. So for this to be positive, you asked for the second and third terms are positive, and the first term positive forces us to this condition that k cube is smaller than 4h minus 1 m square. So that is how we get the condition in the second one. The Carter-Pollard improvement comes out naturally here. If you ask when is this positive, that exactly gives you k cube less than 4h minus 1 m square. Okay, so that is actually the entire proof of this combinatorial lemma, and combining with these tails, one can get the Tusnadi type lemma, and that's the end of the first proof. Okay, I'll stop here.
Okay, are there any questions or comments? Someone wants to ask, they can unmute and ask or post it in the chat.
So Manju, I have a, sorry, yeah, go on.
Go ahead.
Shivag, please.
So I had one question on the coupling proof, the coupling lemma, that is the broad probability x bigger than f of the previous slide.
Yeah.
Yeah. So that this fact, how easy is it easy to see the previous fact? That is x and y are two random variables. No, the next one, next page.
So this is this page, right?
Yeah. How do you show that fact? Is it easy to see that immediately?
Oh, this one? This you mean this fact easy to prove, that one?
That's right. Yeah,
okay,
right.
So no, it is easy. I mean, as I say, you couple them using uniform. You take a uniform random variable, and how do you simulate an x starting from a uniform variable? Of course, you can break it in the interval 0, 1 in bad ways, but do it in the most natural way, do it in an increasing way. So you take so let's say the mass function is alpha 0, alpha 1, alpha 2, etc. So you take the smallest interval 0 to alpha naught as when uniform falls in 0 to alpha naught, you say x is 0. When alpha naught to alpha naught plus alpha 1, you couple like this. And you use the same uniform to do
very nice. Okay, very nice. Thanks.
Kaushik, you want to ask your question?
Yeah. So, so Manju, after you showed these estimates on the tails, so you mentioned that then for large k, that information theory bound, No, is that step also like what is involved in that step to go from? I mean, is once you prove the tail?
I mean, to prove these things or to use these things? What are you asking?
No, so for you.
Okay, so actually this itself will suffice to prove for large enough k. So, sorry, this type of estimate will suffice to prove the lemma for large enough k, when k is kind of proportional to n.
Correct.
There are actually 3 regimes or so that work. Okay, so there are some 2-3 regimes. So once you prove it there, you have to kind of do a bootstrapping. I mean, you have to use the fact that you have proved the tail from, you start at the end, at the far end of right tail, you use this estimate to prove it, because this factor, which is polynomial factor, is swept away by the exponential one. So that will not matter in the far tail. Okay. But then you can go up to some point, then from there you have to bootstrap from there to some other point. And then there are 3 regimes. So I don't know to explain it too well. you have to take it to the sums actually. So so in some sense, what happens? Okay, so here we have comparison, right? So suppose you have proved this for some. Suppose you have proved this alpha m bar of k is less than equal to beta m bar of k for some k naught.
Yeah.
Okay, so some k naught you have proved. Then suppose I want to go to k naught minus 1. What should I try to do? Here I have to, in alpha m bar of k naught minus 1, I have to add one extra term, namely alpha m of k naught minus 1. In beta m bar of k naught minus 1, I have to add one extra term. Okay,
Yeah.
but actually this mass function tells you that you have to go a little before. So you have to work with the fact that these gaps between these are reducing. Okay, maybe it's not a clear enough explanation. Let me not try to say it fully.
Okay, I mean, maybe I can just look at the paper. Yeah, I mean,
I can explain.
Okay.
Yeah,
Okay.
it takes a few minutes to
No,
explain.
no, okay, I get the rough idea, but yeah, so you kind of have to switch between the two ones, right? Because you're for alpha m, for going for beta m, you are going down. So that means that for k minus 1, you have to go back to the blue estimate and come back, keep going between the.
Yeah, so let me just say it once more in another way. Suppose I have these estimates of the mass function, alpha m of k greater than equal to beta m of l. Okay, so suppose I want to sum the tail of beta from some L naught to beyond. For each of those points, I can use the corresponding k, right? For each L naught plus 1, etc., I can use the corresponding k.
Yes.
Which is like this. But this won't be an injective thing. Several different L's get mapped to the same k. Because this is, I mean, this is getting compressed.
Right.
So you have to argue that you have to argue against that overlap. That's what you have to do. Otherwise, by summing them, you would have gotten the answer. So L naught, so if you take L from L naught to N, that corresponds to K from L naught minus L naught cube over M square minus 1 to N. But that mapping is not 1-to-1. So you have to kind of overcome that.
Okay, thanks. Yeah.
Manju, this is Naveen here. Can you hear me?
Yes.
Yeah, recently I found like a tail bound for like a binomial, which was quite tight and like might be useful if you can try it maybe.
So
may not have
so very tight bounds are known for binomial. Okay, so I would like to see, but something that works here, we need something very sharp. I mean,
very sharp. This is quite sharp actually. It's like I'll send you a reference. It is
okay. So there is also something with kind of ratio kind of going close to 1, but that's also not sufficient for this.
No. These are sharp in the sense of being kind of I will send you a reference.
Okay.
Like, this is something that I found recently.
I mean, in the context of okay, so sure. I mean, even the KMT proof or the polar proof of this use the strong, approximations to the binomial coefficient. Actually, the binomial coefficient can be written as a beta integral. That is one way of getting estimates on the binomial coefficient. You can write it as because of the duality between binomial and beta, you can write it as a beta integral and then get estimates using asymptotics of integrals. And so higher order, which is kind of equivalent to doing Stirling's approximation, higher order asymptotic expansions. But anyway, but there are many steps involved. So I would like to see, we can.
Yeah, this is from 2013, so I don't know if it is. Like I found a paper from 2013 that had like very sharp estimates for this.
Okay, yeah. Sure. Thanks.
Okay, I guess, okay, if there are no other questions, let's maybe take a 10-minute break. We will start at 3:35. Okay.
Okay.
Yeah.
So it looks like I have stopped the sharing. Is that right?
Yeah, you have stopped the sharing.
Okay.
He has not stopped the recording.
Manju, or
yeah, you can stop the recording.
Okay.
So should I start the lecture?
Yeah, I think maybe a minute. It's at 3.
Okay, sure.
We can wait a minute and start. Okay, Manju, maybe now we can start.
Okay.
Yeah. Okay, so welcome back everybody. And so Manju will continue with this second part of his talk.
Okay, sure. Yeah. Okay, so this, as I said, so there are two methods of proofs. By the way, I said there are two KMT theorems, two methods of proof. Probably one can mix and match and prove either either method for either. Here, I'll talk about the analytic method of Chatterjee. Okay, so this was from in 2008. Chatterjee found a really interesting proof of KMT theorem. It was restricted to random walk, simple symmetric random walk. Nevertheless, it's a very interesting proof. So I want to talk about that. So let me just recall what is the KMT theorem. It was there in the first talk. I don't think anybody is here from who was not there, but nevertheless, let me just quickly recap. So KMT for simple symmetric random walk says that if you can couple random walk and Brownian motion, standard Brownian motion, and simple symmetric random walk up to n steps, so that the difference between them is at most a constant log n plus x with probability at least 1 minus e to the minus x. Okay, so this is a very this is log n is the thing. So you can couple them. I did not say anything about the history of these things, by the way. It was soon after Donsker. I did not. So there were people who looked at it. So Strassen and so on. So in fact, if you make less assumptions, so as I mentioned, Komlós-Major-Tusnády showed it for exponential time. What came before that? So there were people like Strassen and so on who looked at what if you don't, if you assume less. If you assume only up to 4 moments exist in xi, what is xi here? Sn is sum of x1, x2, xn. Okay, xi are the steps of the random walk. If xi have only 4th moment or something, then you get something much worse. Actually, it is not log n; it is a power of n and so on. So it is better than saying just square root n, but it will not be as small as this. It will be some power of n. So that and then there were several improvements, and then this was apparently quite surprising. So people showed that couldn't be improved, and then Komlós-Major-Tusnády came ahead and came over and showed this theorem. Okay, so what is Chatterjee's approach to this theorem? Okay, again there are two broad steps are the same. He has this univariate coupling lemmas, and he has a step going from coupling univariate coupling to that of paths. So the univariate coupling lemmas are exactly like Tusnady's lemma. I will show them explicitly. That's what we are going to prove now. Okay, so instead of that, he proves coupling. What are they? They are about coupling binomial distribution and hypergeometric distribution to Gaussian. Okay, that will be the subject of the rest of the talk. Precise statements will come. In going from univariate coupling to paths, I mentioned that instead of the dyadic approach, which is often used, Chatterjee used a different method of induction. And here is his induction step I have given. Well, he doesn't need a certificate, but you can agree that it is quite a smart induction statement. So what is the induction statement? It is a statement like this. It has to be framed exactly correctly so that induction works. Otherwise, you will not be able to carry out the induction step. So what his induction statement is that not about random walk, but random walk bridge. What is random walk bridge? Random walk bridge is random walk with the last point condition. The location at time n is conditioned to be some t. Okay, Sn is conditioned to be t. That's a random walk bridge. Analogously, Brownian bridge, which is Brownian motion, it's not the standard Brownian bridge, it's Brownian motion conditioned to be t at time n. So the induction statement is that for any value of t for which this has positive probability, Sn equal to t has positive probability, you take any such value of t, then there is a coupling of the random walk bridge with the Brownian bridge such that the maximum difference m and t between the two paths in this coupling satisfies this exponential moment bound. That e to the lambda m and t expectation is bounded by this e to the a times log n plus b lambda square t squared by n for all lambda smaller than equal to some lambda naught. So here the statement is that he fixes lambda naught a and b. They are fixed to start with, and this is the entire induction step. And so you have to do this induction. You have to do induction on n in this statement. So This is quite nice and it works. In some sense, there is a sort of dyadic sort of thing, but what he does is that, how do you do it by induction? So you first you are trying to couple random walk with Brownian motion, right, up to n steps. So let's say you couple Sn with Wn. That you do by the univariate coupling lemmas, right? You couple them by univariate coupling lemmas. And then this bridge, then you have this, sorry, that's not, okay, sorry, that's not correct. So you have to do it in the induction statement. How do you do it in the induction statement? So if you want to do it, assume it for all smaller n, then what happens is if you condition on the midpoint, what happens in this, you are looking at a random walk bridge and Brownian bridge of time length n. You see what happens at time n by 2, condition on that. Then you get the random walk bridge becomes, once you condition on what happens at n by 2, you get 2 independent random walk bridges and 2 independent Gaussian bridges, Brownian bridges. Okay, from 0 to n by 2 and n by 2 to n. Now, by inductively, they can be coupled. And by the univariate coupling lemma, the value at n by 2 can be coupled. So this is the gist of the induction proof. Okay. So we will not talk about this part. We will just go to talk about the univariate coupling lemmas. Okay. What is the coupling lemma that Chatterjee proves? So he has two, as I mentioned. One is for binomial, one is for hypergeometric. I will explain them. Let me explain what are they. So Sk is x1 plus up to xk as before. So the way to interpret what is binomial, what is hypergeometric, one way of thinking about it is you have a box with n coupons, let us say. Okay, box, sorry, no, not with n coupons, box with an equal number of plus 1 and minus, let's say n is an even number, equal number of plus 1 and minus 1 coupons. And then you sample from it with replacement. Then you get i.i.d. Bernoulli, plus minus 1, right? So these are partial sums of that. Okay, well, okay, that's just an unnecessary explanation. Now let me say, what is the binomial coupling lemma? He says that you can couple Sn with z root n in such a way that this exponential bound holds. Okay, what is it? Sn minus z root n absolute value and exponential tail, exponential moment of it is uniformly bounded. So there is a theta naught kappa naught, which are just fixed numbers. You can give some numbers, it's not important. They are positive fixed numbers such that this happens. So obviously this means very strong bounds on Sn minus z root n, right? It can't be too different. Because, I mean, in fact, it's of unit order. So it is also saying, like in Tusnady's lemma, that two random variables of standard deviation square root n are coupled within unit distance. Why within unit distance? You can just apply Chernoff here. What's the probability mod Sn minus z root n deviates by more than x? You just plug it into this, you get some e to the minus theta naught x. So it gives that. However, so this actually follows this, by the way, this binomial coupling lemma trivially follows from Tusnady's lemma. Because what Tusnady's lemma says is that Sn and z root n can be coupled so that their distance is at most z square plus some constant. Now, z square has exponential moments. Therefore, in that coupling, certainly this is satisfied. This lemma is satisfied because e to the theta naught z square, for small enough theta naught, it is finite. You cannot do the other way. This lemma is actually strictly weaker than Tusnady's lemma because unlike in Tusnady's lemma, this is not telling you, in Tusnady's lemma, you relate the smallness, I mean, the closeness of Sn to z root n is not related to z. In Tusnady's lemma, you say that if z is small, then the difference is also small. And if z is large, difference is allowed to be large. But here in this is an overall expectation. You don't know where the difference is coming from. Sn minus z root n, the difference where it comes from, it may also happen for small values of z. So that is the reason this you cannot get Tusnady's lemma from here. It's weaker. Okay. So sort of to compensate for that, but also for another reason, other reasons, he needs another coupling lemma. This is not the only lemma. There is another univariate coupling lemma for hypergeometric distribution. Let me explain that also. Let me explain the results. Then I will explain the method of proof. Most important point is the method of proof, and I'll say more about that. So what is the coupling lemma for hypergeometry? What is hypergeometric distribution? Here for me, it just means this. You have a box with n coupons. Okay, so the box has n coupons. Each coupon is labeled +1 or -1, but we have n plus s over 2 coupons labeled +1, n minus s over 2 coupons labeled -1. That means the difference in the number of plus ones and minus ones is little s. That is this parameter small s. So this is the box. And then you draw now without replacement. You draw k coupons without replacement. So one by one. So in other words, you draw k different distinct coupons from this box and you calculate the sum. That is this random variable sk of ns. So k, n, and s define the box. N and s define the box. N is the number of coupons, s is the excess of plus 1 to minus 1, and k is the number that you are drawing, number of coupons that you are drawing. So sk of ns is the sum of those. It is what, okay, this is a hypergeometric in the sense, okay, it also takes negative values. It's just a affine shift of the usual hypergeometric. Now, sk of ns is not centered. What is the expected value of sk of ns? Each coupon on average is s by n is the expected value of each coupon. Therefore, you should subtract k times s by n to get a centered random variable. So that I denote wk of n comma s. It's the centered version of sk of ns. That's all. This is what you subtract. Its variance I have written for just to show that its variance is k into n minus k over n minus 1 minus s squared over n squared. It may be useful to think of this. So if you say p is the proportion of ones in the box, that means n plus s over 2n. N plus s divided by 2n. So yeah, so here, so if I say p is the proportion of coupons, okay, so it's too painful to write, I won't do that. So if p is the proportion of plus coupons, then this is actually 4pq, that's what it is, okay? So, okay, so 4pq times k into n minus k over n minus 1. And then we introduce one notation, sigma nk square is the variance when s is 0. That is for the unbiased box where you have equal number of plus and minus coupons. So that is same as variance of sk of n0 or wk of n0. They have the same variance. So that is sigma nk square. So these are the notations. And Chatterjee's hypergeometric coupling lemma is this, that you can couple wk of ns. So wk of ns is this with sigma nk times z in such a way that this potential moment bound holds. Okay. So what is this saying? So there are some conditions. So again, this is holds for all theta less than equal to theta 1. So theta 1 and m1 are some fixed constants. You can write down, but not important what they are. They are positive finite constants. And this holds for all k which are comparable to n. Here Chatterjee writes it's for n by 3 to 2n by 3. So I also write the same. But all you need is for k close to n by 2. You can think of always k as being half of n. That is roughly how he applies it. Okay, when in the application to KMT, you can assume k is n by 2, the nearest integer to n by 2. It doesn't matter, but you can also allow it to be between a little wider range. But one needs to explain a little bit here. This is not always a good coupling in the following sense. See, we are comparing wk of ns with a Gaussian of variance, which is variance of wk of n0. So it's not the variance standard deviation. Sigma nk is not the standard deviation of wk ns. So when s is 0, this is saying something exactly like when s is 0, this is saying something exactly like the binomial lemma. Why? When s is 0, the right side is just a constant, e, right? So that is exactly like this. So you are saying that wk of n0 and the Gaussian with the same variance can be coupled within unit distance. That's what it is saying. But it is saying something more, that when s is not 0, it is not coupled well, because this can be big. You see, small s can go as big as n. So the difference in the number of ones and number of minus ones can be as large as n. So this quantity on the right side can be big. S squared by n can be quite big also. So, but it is the controlling parameter. So what it is saying is that this may not be this. Of course, you don't expect wk of ns to be close to sigma nkz because they don't have the same variance. But the controlling parameter is exactly this s squared divided by n. So, for example, if s is smaller than square root 10, then you still have a good coupling. Okay, if s is smaller than square root 10, which is then the right side is still a bounded quantity and you have a good coupling of this. So if you have a box where the number of ones and minus ones differ by square root 10 and you draw k, which is approximately half n number of coupons, you are still getting a good coupling, which is to be expected. But this is the gist of so these two lemmas, binomial coupling lemma and the hypergeometric coupling lemma, are the key points of the first, the main step of Chatterjee's proof. Okay, how do I send this away? So does everyone see this control panel here? No, okay.
No, Manju, no, see only the cursor now.
Okay, fine. No, I was seeing that some control panel was there, but I removed it.
No, control panel probably is only visible to you.
Yeah, I shared only the application, so you're right. So, okay. So these are the two coupling lemmas, okay? So the binomial and the hypergeometric coupling lemmas, okay? So now again, what we are going to do is we say that you can do this by Cauchy criterion. Don't compare binomial to Gaussian, hypergeometric to Gaussian. Compare binomial with binomial and hypergeometric with hypergeometric. So these are our versions of the Cauchy criterion. So in other words, if you prove this by Cauchy criterion, you can get Chatterjee's two lemmas. So let me explain that. So what is the first one? It's exactly like the binomial coupling lemma, except you are now coupling 2Sn with S4n. Instead of Sn with Z root n, you are doing this. But otherwise, the statement is exactly like the binomial coupling lemma, where you have this exponential tail bound. We are saying that you have this. Okay. For the hypergeometric coupling lemma, it's again very similar statement. So theta, there are some constants, theta 1, kappa 1, m1, and then k is always comparable to n, like between 1/3 n and 2/3 n. And then you have these three. I have broken that statement here in Chatterjee's to two different statements. One of them is like the binomial coupling lemma. What is that? You compare the hypergeometric with k and n with hypergeometric with 4k and 4n. Okay, so instead of 1 is with a box of n coupons and 0. N0 means equal number of plus and minus coupons. So first take the unbiased case where you have equal number of plus and minus coupons. You consider one box where you have n total number of coupons and you draw k of them, where k is, let's say, like n by 2. In the other case, you consider a box with 4n coupons and you draw 4k of them, roughly again half of the total number of coupons. And the first one is exactly saying that those two can be coupled after scaling, because W2 is going to be like 2 times W1. So the 2W1 and W2 can be coupled so that they are unit distance apart in this exponential tail bound. Okay, this is the first statement. The second statement is about what happens if you are not, how does the unbiased case compare with the biased case? So W is the biased case. Okay, I don't know why I have written this. Sorry, this is a mistake. There is no subtraction here. W is already, Wk of ns is already something that where we have subtracted the mean. So there is no extra subtraction of sk over n. This is a typo. So W equal to Wk of ns and W1 is Wk of n0. So you have two boxes, n coupons, but one is biased, one is unbiased. What is the difference between, how can I couple W1 and W? Then it says that you can couple them exactly with this controlling parameter. This exponential moment is bounded by e to the theta squared s squared by n. S is the bias, right? S by n is the difference in the proportions of plus and minus. So s squared by n is the difference. So the controlling parameter. So I will not try to explain how you can get these lemmas from there. This is exactly like before. Once you have this, for example, here you have Sn and S4n, then you couple S4n and S16n and so on. And then you can put together all these things with the Holder's inequality and get this binomial coupling lemma. Similarly, same here. Once you have these hypergeometric couplings within themselves, you can just go from kn to 4k, 4n, 4 square k, 4 square n, and so on and do that. I will not repeat that sort of proof here. What I want to indicate is only how we go about proving the binomial coupling and hypergeometric coupling lemma. Okay. So this finishes the statements of the things that we want to get to. The interesting thing here is the method. Okay. Okay, let me say my remark on this probably is irrelevant, but so I think that the first proof, the combinatorial, whatever simplification there is, I feel that that's sort of an expository kind. Maybe instead of with something that you could not present in class, you can present in class. But here I think there is actually, at least to me, there was a simplification of understanding also by doing this. because you go from a rather complex situation to finite states Markov chains. That is what happens here. Okay, so here the point is we are coupling distributions on integers using Markov chains. This is what I want to explain. For the moment, forget all this Tusnadi lemma and so on. The question is, I have two probability distributions on integers. How do I couple them using Markov chains? Now, I will actually not explain Chatterjee's method because, I mean, what he did, it's kind of complicated to explain and it won't help me in explaining mine. So I will just explain the simplified. At some point, maybe I will indicate it is all inspired by that paper of Chatterjee. Okay. So what is it that we want to do? So the general strategy, let me outline. Alpha and beta are two probability distributions on integers that we want to couple. So don't worry about some pathological cases. Think of them as finitely supported probability distributions. We are not interested in any tail behavior and so on. So for example, the two cases we want are alpha is the distribution of 2Sn and beta is the distribution of S4n. That's what we want to couple. They are both probability distributions on integers. How do we couple? For that, the idea will be to first thing, what we will need is nearest neighbor Markov chains on integers whose stationary distributions are alpha and beta. In other words, you want a Markov chain on Z nearest neighbor. So you are allowed to move only from I to I plus 1 or I minus 1. Okay. All my Markov chains will be continuous time, by the way. I will only work with continuous time Markov chains. But you only transition from I to its neighbors, I minus 1 or I plus 1. So I have to, for this method to work, I need a Markov chain with stationary distribution alpha and a Markov chain with stationary distribution beta like this. What does that mean? So you can't have gaps in the support, for example. You cannot have, so for example, you look at S4n. S4n puts mass only at even integers. It has gaps. So you can't actually have a Markov chain whose stationary distribution is the distribution of S4n. 2Sn is even worse. 2Sn, if n is an even number, then it takes only multiples of 4. So it has gaps, bigger gaps. So you can't actually have Markov chains with those stationary distributions. But well, what we can do, so how do we deal with such situations? It's easy enough. So S4n you just divide by 2. Since it's all even numbers, if you take half of S4n, then its support is exactly all integers from minus 2n to plus 2n. So there is no problem. So as long as your support is a contiguous set in Z, we can find a Markov chain with that stationary distribution. Okay. What about Sn? Now I have scaled S4n by 2, so I have to scale 2Sn by 2. I can't scale it by something else. So I have to look at Sn. Sn does have gaps. Now it has gaps of 1. Okay, Sn will have, if n is odd, it will have, in any case, it will have gaps of 1. Okay, it takes either odd integers or even integers. But to modify that, what we do is, so to get a Markov chain which has that stationary distribution, we can't. So we add to Sn a one random variable r. R will always denote a random variable which takes just 3 values, minus 1, 0, 1 with probability 1/4, half, and 1/4. Just okay. It's just one distribution. You can do a lot of things here, but by adding that, we can get rid of this periodicity. So Sn plus R will have a full support. Sn was supported from minus n to n, but only alternate integers. But Sn plus R will go from minus n minus 1 to n plus 1, and every integer will be in the support. Okay, so good. So then there will be Markov chains with whose stationary distribution is Sn plus R. Okay. And this makes no difference for us because what we wanted to do was couple 2Sn with S4n or equivalently half S4n with Sn. But Sn is very well coupled with Sn plus R within distance 1 because you are adding a random variable which is at most 1. So you can as well couple Sn plus R with half S4n. So this kind of preliminary preparation may be required in actually applying this method. That's all the point of this. Nothing deep here. So even in hypergeometric situation, you may need to do this. You may need to scale, you may need to add an additive perturbation, etc. So if you have gaps of length 3, then you add a random variable. If you have gaps of length 3, then you add random variables which take support in minus 3 to 3 to kill the gaps. That's all. That won't affect much. But so let's always assume that alpha has finite connected support on integers. Okay. So let's take one such thing. So there are many Markov chains whose stationary distribution is alpha. we are going to make a choice. I mean, by Markov chain, I always mean nearest neighbor Markov chain. So transitions for from I to I minus I plus 1 or minus 1. I don't know why I have, okay, I know why I have done that, but this lambda I plus is the transition rate from I to I plus 1. Lambda I minus is from I to I minus 1. This reversal of plus minus should not have been here. Okay. So, but there are many chains like that, even many reversible chains. You can write down reversibility equations. There are lots of reversible chains with this stationary distribution. But one can do it at that level. In the paper, to a certain extent, I stay with general Markov chains. But here, let me specialize to the chains that we actually use, which I call Ehrenfest-like chain. So because they are like the Ehrenfest chain that we study in Markov chain class. Okay. What are these Ehrenfest? What is the Ehrenfest chain? Okay, I will. Okay, maybe I tell you what is the Ehrenfest chain first. The Ehrenfest chain is this one where you have a you go from you have a box with n particles and there is a partition. So maybe k of the particles are on the left and n minus k particles are on the right. And at each time point, you pick one of the particles at random and move it to the other side. So k becomes either k minus 1 or k plus 1 and with certain probabilities. Here I do the same in continuous time. So, okay, anyway, so I'll come to Ehrenfest chain. What is Ehrenfest-like chain? I want the lambda I plus, the transition from I to I plus 1 happens at rate t of I plus minus I. Okay, and transition from I to I minus 1 happens at, here the plus minus reversal is correct, by the way. So lambda I plus is the I to I plus 1 transition. That should be t of I minus I, and I to I minus 1 should be t of I plus I. So there is one function t defined at each integer, so that the transitions look like this. That the transition rate means you wait for an exponential with that rate and then jump, right? So that is what it means. So this is what I call Ehrenfest-like chain. So the standard, so if you take the binomial distribution, then the standard Ehrenfest chain is the one whose stationary distribution is the binomial distribution. Okay, so we'll come to that when I come to the true Ehrenfest chain. But if you take an alpha, will such a chain exist? That is a question one can ask. We have already assumed alpha has finite connected support, and you want alpha to be reversible under these rates, t of I. So we have to find a function t. Okay, that is the question. Can I find a function t on integers such that this will be this Markov, this alpha will be reversible for that for these rates? The equations are just given by this. Alpha I, this is alpha I into the rate going from I to I plus 1 should be same as alpha I plus 1 times the rate of going from I plus 1 to I. Okay, so these are the reversibility equations. So can we find t to solve this? Well, so you take the, for example, you take the right end of the support. You can figure out from there. So suppose the right end is some point I. If I is at the right end of the support, t of I has to be I or something. Any questions?
One question from BV is the boundaries are reflecting?
No, I mean, I have to define, well, the Markov chain is only on the support of alpha. Yes. I mean, I have to define the transition rates. Yes.
Okay.
So there are no observing states. It is yeah. So this Markov chain, if alpha is supported on minus n to n, let us say, this this will have transitions, or there are no observing states. Okay.
Okay.
So when you are, yeah, I don't exactly know whether to say it is reflecting or not because I'm not very clear. But what I mean is the Markov chain is supported on the support of alpha, and it is actually irreducible here. So at the right end point, you know what t of I has to be, okay? And then you can successively solve for t all the way to the left end point, but there will be one more equation to satisfy, and I will skip the steps. It will be satisfied if and only if alpha has 0 mean. So this is how you satisfy t, okay? So at the right end point, t of I will be just I. And then you can solve a t of the left, one vertex to the left of it. You use these equations and keep solving till the left end point. At the left end point, there will be one more equation that is satisfied if alpha has 0 mean, and it won't be satisfied otherwise. So this t exists if and only if alpha has finite connected support and zero mean. Okay, so this T is called the Stein coefficient of alpha. Okay, so it by definition it only exists for such distributions. So for example, if you take S4n by 2, okay, then certainly it has zero mean and it has connected support, right? Everything from -2n to 2n, all integers from -2n to 2n. So it has mean 0, so it will have a Stein coefficient, and its Stein coefficient is this constant. T of I is just constant 2n. This is the true Ehrenfest chain. In the usual way, the state space is 0 to n, and your transitions are something like I plus 1 and n minus I or something like that. But here it will be 2n plus I and 2n minus I basically for S4n by 2. Okay, so this is the Stein coefficient being constant is the characterizing statement for binomial half. I have stated that in the next slide. We will come to that. What about the other random variable we were caring about, Sn plus R? Sn is a binomial. It has gaps. It won't have Stein coefficient. But we add that random variable R, which takes -101 with some probabilities, right? So we can calculate the Stein coefficient of that. And it's a simple enough calculation that it comes out like this. Okay, I must say here that there is a small confession. So I say simple enough calculation. I can never guess this thing. So I used Mathematica, MATLAB extensively. In this entire work, I used it at least for 500 or 700 hours, I think. Because I always check on that and then make a guess and then verify it. So, I mean, it was needed for all the statements in the first part of the talk also. I should have acknowledged that. All the lemma that I got and all the comparisons, I only guessed by doing a lot of MATLAB simulations. So here also, I first checked on MATLAB and found this form, and then it is easy to verify. So it turns out that the Stein coefficient for Sn plus R is actually something like this. You see, it is more, so this is the random variable which we are trying to couple with this. You see the Stein coefficients are kind of close. This is constant 2n for the first one, whereas here it is 2n plus a little bit. In this, for j minus n even number, it is 2n plus 1. For j minus n odd number, it can be big, but it is like j squared over n. For small j, it is small. So this j squared by n is exactly what shows up in the Tusnadi and everywhere. That is the quadratic that is showing up actually. Okay, this is simple calculation from this general formula. One can do it, or just from the defining equations. Okay, so this is an example of Stein coefficient. Why Stein coefficient? This is all coming from Stein's method. So in Chatterjee's paper, he never mentions any Markov process, although they are always there in the background. But he talks about Stein coefficient. So let me just quickly say what is Stein coefficient. Let me skip the Gaussian part. So many of you may be familiar with Stein coefficient in the Gaussian situation. But here, let me just explain why we call it Stein coefficient. This is the Stein's equation for the analog of Stein's equation for binomial distribution. I don't know who first did it. I mean, it's actually simple enough. But so this is the equation for Stein equation for binomial. In other words, if W is any random variable which satisfies this equation for lots of functions G, then that W has to be a Gaussian, has to be a binomial with this n comma half distribution. Okay, that is the Stein's characterizing equation for binomial. Now, what does that have to do with the Ehrenfest chain? The Stein equation, the original Gaussian Stein equation, actually comes from the Ornstein-Uhlenbeck generator. Similarly, the Stein equation here is nothing but the equation coming from the generator of the Ehrenfest chain. The Ehrenfest chain has this generator. Okay, you can go from, okay, I don't know why I have written I plus 2, maybe it was normalized differently. For the usual with gaps, I guess it is. Maybe you think of this as I plus 1 and I minus 1. Okay, this is all just impressionistic. So it goes with rate n minus I to I plus 1 and with rate n plus I to I minus 1. So the generator looks like this. And what is the general fact about stationary distribution? Whenever you have a stationary distribution for a Markov chain, it says that the generator applied to any function has zero expectation under that stationary distribution. That's the way of writing. It's a Kolmogorov forward or backward, one of those equations. So this equation is actually the same as this thingy, okay? Except this is written for the difference function. That's all. I mean, it's not, LH is not the same h here, that g will be the difference of this h or something like that. Okay. So that is how the Ehrenfest chain is related to the Stein equation. And what does this have to do with this Ehrenfest-like chains? So suppose your alpha distribution alpha has an Ehrenfest-like chain. That means you have this Stein coefficient t. What that means is that your Markov chain generator equation will become this. Instead of n there, you have this t, which t is a function of the space. I should write t of w. Or it can be t of, yeah, you can write t of w if you want. So t is a function, it's a random variable, it depends on w. So instead of the constant n in this binomial, you have this t, okay? And so if you were to try to apply Stein's method here to show something is close to binomial, you would be trying to show that this t is close to a constant n. That is what Stein's approximation to Gaussian and so on do in Stein's equation. That's what you do. But here we want to show, so that's what it is. The closeness of t to constant relates to closeness of w to Gaussian. So that is the sorry, I should w to binomial. This is wrong. This is cut paste from here. This is w to binomial. Now this is the standard method for Stein's method, but this is Chatterjee's innovation that he could use it for other things like concentration inequalities. I think he was the first to do it for that, and also for this kind of strong embedding. I think nobody did it before Sir Chatterjee. So this is his method. Okay. So that is exactly the point of relation. That's why we call it the Stein coefficient. Okay. I have a bit less than 10 minutes. So let me explain how this is to be done. Now, how do you, okay, so fine. So you have two distributions, alpha and beta. Let's just take the binomial coupling where you are trying to couple S4n by 2 and Sn plus r. You have found the Stein coefficients, which is equivalently, you have found two Ehrenfest-like chains with these as stationary distributions. Now, how are you going to couple alpha? What is our objective? Our objective is to couple alpha and beta using these Markov chains. So I have to construct a joint Markov chain on Z2. Okay. So how do I get a coupling of alpha and beta? So I explain that now is in a general form. At the moment, this slide doesn't have anything to do with the Ehrenfest-like chains. So suppose alpha and beta are stationary distributions with transition rates lambda I plus minus and mu I plus minus. Okay, these are nearest neighbor continuous time chains on integers. Now we define a Markov chain on Z2 that will couple, whose stationary distribution will couple alpha and beta. Okay, that's what we are going to do. How to do that in a nice way? The basic idea is very simple. You have two Markov chains on integers, right? So you try to move both of them together. Coupling means you try to move them together to the right or together to the left as much as possible. Avoid moving in opposite directions. This is the general recipe. Okay, so this is the recipe which is explained in this picture below, which I will explain now. So try to move as much as possible together, never move in opposite directions. That's the recipe. So what does that mean? So from ij, I will move to one of the 6 possible states here, right? I plus minus 1, j plus minus 1. That gives me 6 different places on Z2 to where I can go. Those are indicated here without drawing Z2 actually. So what I do is I go from ij to I plus 1, j plus 1 with as much possible probability as possible. What do? It's not probability, sorry, these are rates. So with rate lambda I plus min theta j plus, you move. So lambda I plus is the rate for the first Markov chain to move to the right. Theta j plus is for the second Markov chain to move up. So this minimum is the rate at which this Markov chain is going to move diagonally to the right, up and right. Okay. Similarly, the Markov chain individually, they used to move with lambda I minus to the left and mu j minus to the down. So with the min of those two, you move to left and down. That is theta ij minus minus. Now you fill in the rest so as to satisfy this. Now what happens? Maybe lambda I plus is bigger than theta j plus, in which case a little bit of rate is left over. So with that rate, you move to the right. Lambda I plus minus mu j plus, the positive part of it. Okay. On the other hand, if it is, oh, sorry, here I got theta j plus, this should be mu j plus. Okay, sorry, this is a typo here. This is lambda I plus min mu j plus in the right side here, this one. And also here also it is lambda I minus min mu j minus. And if lambda I plus is larger than mu j minus, there is a rate to move to the right. On the other hand, if mu j plus is larger than lambda I plus, you will have a rate to move to the right. Only one of these two blue things will be positive, the other will be 0. Similarly, you can move to the left or down. Okay, that's possible. So this defines a Markov chain on Z2, and its generator is given like this. This is the generator of the Markov chain, theta ij plus plus f of I plus 1 j plus 1 minus fij, and so on. This plus circle means the I increases, j doesn't increase. Circle plus means I doesn't increase, j increases. So that's what I have written. That's the generator of this Markov chain. So this is very natural, right? In Chatterjee's paper, he doesn't mention Markov process, but he constructs an elliptic differential operator and he has to find a solution. And ultimately, there is a degenerate solution he finds, which is basically this idea that you try to move the Markov processes together as much as possible. That's the idea there. Okay. So with this, what happens? So how do I couple using this? So now this is the generator. First of all, let us say this Markov chain is usually not irreducible, but it will have a unique recurrent class. So there will be a unique stationary distribution that I denote gamma. So this joint Markov chain has a unique stationary distribution that I denote gamma. Okay, I want to first tell you that gamma is a coupling of alpha and beta. That is easy. So what is the basic equation? So if L is the generator, then under the stationary distribution, E gamma LF is 0 for any F. Okay, that is the Kolmogorov equation. So what Fokker-Planck or whatever it is. So if you take F to be a function of X alone, so take Fxy to be phi X, then this entire thing simplifies drastically because see, you have where j changes, Fij plus 1 and Fij, they are the same. So these terms like this will become 0, right? So only where I term, the first coordinate differ, you get something. So overall, you will just get this, which just means that if you apply this E gamma LF equal to 0, it is telling you that the first marginal of gamma is alpha. Okay. So this is actually the generator for the X chain, for the chain corresponding to alpha. So this tells you that the first marginal of gamma is alpha. And similarly, the second marginal, if you take a function of y alone, you will see that the second marginal is beta. So you have a coupling. Is it a good coupling? That is the thing that we have to investigate. Why is it a good coupling? Intuitively, it was good to try to make them together, but quantitatively, how does it translate? For that, we have to keep track of how X and Y change. Suppose X and Y are coupled, will they stay close? Okay. So for that, you do again the same type of idea, but now you plug in functions of X minus Y. Okay. Suppose Fxy is a function of X minus Y alone, and then you again apply it in this Fokker-Planck equation, E gamma LF of Z equal to 0. Well, you write some, so you get many things, you get many terms. You can simplify it. This is an equality. I won't try to explain because this is anyway an identity. I have rearranged it in some way. What is it? On the left side, you have, the original was phi of X minus Y, phi of the difference. Here it is written in terms of psi, which is a first difference of phi. Okay. So Yogesh, I have 1 or 2 minutes. So can I go extra 3-4 minutes? Is it okay?
Yeah, I think maybe it's okay. You can take extra 2-3-4 minutes. Yeah.
Okay. Sorry about that. So so psi of h is phi of h plus 1 minus phi h. It is a difference of that, and a and b are some things built out of the rates. In some sense, a and b are 0 if lambda plus and mu plus, lambda and mu were the same. Okay, if the rates were the same, then they would be 0. But otherwise, they are some measuring the difference in some way. You don't have to pay attention to the exact form of it. But when we specialize to the Ehrenfest-like chains, this A and B simplify to some extent. And what I get is that equation becomes this equation. Okay. That E gamma of Q minus H, have I defined what is H? H is the difference of X minus Y. Okay. H is the difference of the two things in the joint Markov chain. So it is giving an equation like this, that a function of H, it's giving an identity like this. Okay, so I can't explain this too well. It's just an identity you get. This is just a simplification of the previous one when you restrict to Ehrenfest-like chains, because there this A and B simplify. Now the point is just to plug in various functions. This is what Chatterjee does in his situation also. You plug in various functions of psi and get bounds on what we want is tail bounds on H. you want a coupling of x and y, so this Markov chain gives you the gamma is a coupling of x and y, and h is the difference between x and y. We want something like, what do we want in the binomial coupling lemma? We want exponential bounds, exponential moment bounds of h, right? So that is what we want. So we want to be able to control things like e to the theta mod h. Okay, e to the theta mod h. We want to get bounds on that, and for that you just have to plug in various functions into this equation, master equation, and you can get various things. So it's a very simple example I have plugged in here. You take psi x, which is indicator of x greater than equal to a. Okay. So then what happens on one side, this h minus part vanishes. You get e gamma h plus indicator h greater than equal to a plus 1. That is this one. There should be a factor of 2 maybe here. It is less than equal to what is on the right side, q minus a plus. Okay, so you get something like this. So if you have a control on this q, then you get a control on h. That's all. So for example, probability h is at least a plus 1 can be bounded by the expectation of q minus a, positive part. For example, if the two Stein coefficients s and t are close, then you get a good bound. So an example is worked out here. You take that same half of S4n and Sn plus r, the binomial situation. There the Stein coefficients differ by, one of them is Stein coefficient is just constant 2n. In the other one, it is 2n plus this extra bit, right? So what is the difference in the Stein coefficients? This q function, the difference in Stein coefficients is basically j square over n plus 1, or in other words, y square over n plus 1 plus 2 at most, which has exponential tail. So immediately from this equation here, you see that h has exponential tail bounds. Okay, because q minus a positive part means at least q has to be bigger than a, right? So y square over n plus 1 bigger than a, that has exponentially small probability. So this is how you get this immediately gives you the binomial coupling lemma. This also gives you the first part of the hypergeometric coupling lemma, provided I compute the Stein coefficients of the hypergeometric distributions, which is also doable. I have done this in the paper. Okay, I will just say that this won't suffice for the second part of the hypergeometric coupling lemma. There, it's not what that will give me. I need bounds like this. So the bit that is missing, if I just do it in a naive way, you get this, you will not get that sort of bound. I need a bound in the second part. I will need a bound that has this theta square in the exponent. Okay, so here in this binomial and so on, you just get a constant upper bound for the exponential moment. But for the second one, where you compare the hypergeometric and the biased hypergeometric, you need a control on the exponential parameter on the right side. So you need a strong bound like this. And I had given a proof of that here using a kind of the proof of this again follows from here. You have to plug in some functions into this one. You have to plug in the appropriate function psi into that. And basically the function psi you plug in is an exponential. But then you need a little bit of trick. So it's a sort of generalized form of Holder's inequality, or if you want, it is convex duality. Using that, we can get bounds like this. Exponential of theta times the difference, you can bound. The main point is that the difference h in the Markov chain of x and y is bounded in terms of q, which is the difference of the Stein coefficients. This is the moral that you have to take home. Okay, so this is the very last slide. I will end this, sorry, with this. So the hypergeometric is a little complicated to write down. So I have just written the same for the binomial. Instead of comparing hypergeometric with biased hypergeometric, I have written it here for binomial with biased binomial. So if you take binomial n half and binomial np, then you will see all the features that are there in the other lemma. So because the binomial n half, the Stein coefficient was simply 2n. Whereas for binomial np, the Stein coefficient is 2np plus 2pqn plus a linear term, q minus px. So in this case, if you try to use the Markov coupling and bound the difference between the two things, namely h, capital H here, in terms of the q, which is the difference in Stein functions. So the difference in the two Stein functions here, which is n by 2 for one and 2pqn plus q minus py for the other, then you get basically something like this. which can be bounded by this parameter, and that's where the s squared by n parameter comes, where s is the difference in n times p minus q. Okay, so that gives you the difference expectation e to the theta mod h is bounded by this quantity with the controlling parameter s squared by n. Okay, sorry, the last part was rushed. Maybe it was not clear. I will stop here. This hypergeometric is exactly the same. Only one small point. So I use, well, okay, it's not worth remarking. So let me just thank you for listening.
Okay. First, let's maybe give a round of applause to Manju, and then we can ask any questions people can ask. All of you should be able to unmute. Maybe let's now thank Manju. Okay. Any questions or comments? You can unmute yourself and ask, or post it on the chat. I can ask. I don't see any question.
Manju?
Yeah.
So this Ehrenfest-like chain, all you really, so the reason why you needed this contiguous is essentially you have a connected graph. So I guess a similar method can be employed for distributions on connected graphs. Am I correct?
Possibly. I mean, so if you are considering two Markov chains on a common state space, and then you want to couple them, let's say, possibly you can try to do this. I did not see, I mean, I did not check what happened. I mean, you would try to make them move together as much as possible.
Right.
Yeah. So,
but the problem is that. So the problem, I guess, is the fact is that here you have a well-defined orientation or direction or something of this sort, which is not present in the graph.
No, that is itself not necessary. See, if you are on a common state space, and the coupling would do the exactly this. You try to couple the steps in this way. You try to make them move together. Okay, yeah, you're right. Sorry, there is a sorry. The question of difference. Okay, what is the meaning of difference? Okay, so you can do. I mean, Markov chain coupling in very general situations is important, but here we are talking about the whole idea is in the end. This is the what Chatterjee does. I mean, you plug into this equation various things, and you get bounds on the difference. So in a general sense, the difference does not make much sense.
You can look at the distance between, so if you're looking on a graph, if you're working on a graph, connected graph, then you can look at the distance between the state of the Markov chains.
You can do that. You can do that. I don't know if you will always get a, because the distance can change in abrupt ways in a graph, maybe. I mean, or sort of.
Not quite.
I do not know. Okay, let me say I do not know. It's possible that one can get something there also.
Thank you.
I did not think about it. Yeah, certainly one can try on Z2 or ZD, certainly.
That was actually precisely what I was thinking about, that if you, but in Z2, again, I thought that one may be able to employ something similar, but...
yeah, see, by the way, there is all this whole business of multivariate KMT, which is actually complicated. I don't know much about it. And it is on a long list of things to do and not at the top. So I don't know what, I mean, so I don't know if this method will be of any help in such situations, but maybe or maybe not. So there is the question of multivariate KMT, which is you take random walk in Z2 and try to couple with two-dimensional Brownian motion and all such things, for example. It's actually difficult, I believe. So there's some remarks I have read that this is a bit involved. I don't know much about it.
So maybe I'm missing something. When you're considering random walk in Z2, isn't it something like a lazy random walk in both directions? Okay, not quite. Not quite.
Yeah, actually, no. Okay, maybe is that so? I mean, so
no, it's not. I think I made a mistake.
No, you can think of it as two independent random walks. That is possible for just Z2. But yeah, maybe just for Z2, the thing that I said is okay. But maybe it is not for this, but maybe more general correlated things also. So you can have a, yeah, sorry. I mean, okay, I do not know. So any other questions? Okay.
I don't see any other.
I had one small one.
Yes,
Can you
Shiva.
go back to the second or third slide of this talk? The next one.
Sorry, next here, you mean?
Then one after this. Yeah. So here, you somehow you're able to find alpha and t that satisfy this equation. Is that right? So
no, alpha is given to us. Alpha and beta are given to us, and I have to couple them. So what I do is I look for the chains. Actually, it is not necessary that you should choose the Ehrenfest-like chain. So in my paper, I write it in a general form, but here I showed for it seemed the most natural when you're working with binomial. But when you're working with some other distribution, you would probably choose a different chain. So for example, to show coupling to Poisson, you would probably use a different chain. Okay.
So is this like some sort of the same genre as how we do in Stein's method, or some little different than that?
This is, I mean, so it is, that's what this relationship between Stein's method is exactly what I explained here. So that is exactly the Ehrenfest chain generator is what gives you the Stein's equation for binomial. Just as the generator for the Ornstein-Uhlenbeck process is what gives you the Stein equation. See, Ornstein-Uhlenbeck process here has this generator. And basically saying that expectation of LG is 0 with respect to the stationary distribution, which is Gaussian, is exactly this Stein equation, except that it is written, this will give you in terms of G dash that you call it F, that's all. So that's the Stein equation. And what is Stein coefficient in Chatterjee's paper? Instead of satisfying this one, suppose you are able to satisfy it with something that's not a constant sigma square, but a random variable T. T of W, let us say. The closer that T of W is to sigma square, the closer W is to Gaussian. That is the usual way in which you do normal approximation.
I see. Okay.
But here you are trying to do a closeness in a very different sense. And that is where you use the generator and plug in various functions. That seems simple enough in retrospect. I don't know why these things are not done before. But yeah, so Chatterjee was the one who did it first. So once you write the generator and then manage to write everything, so plug in various functions here in these type of equations. That is what gives you the bounds that you want. Yeah.
Nice idea. Very nice.
Manju, one question is, I forget, it's mentioned in Chatterjee's paper, is the existence of the Stein coefficient. Is it always guaranteed or?
No, even in the continuous situation, it is not always guaranteed. There are some conditions. So Chatterjee proves a lemma that if you have, if it has a density, which is supported on a single interval and strictly positive in the interior, then you get, that is exactly like this one.
Okay.
That
but
is
in
very
discrete
much
also, that's similar, is it?
No, he doesn't do any, in his definition of Stein coefficient, there cannot be a discrete distribution will not have a Stein coefficient. So he has to take a binomial and first add a uniform or something to make it continuous first.
Okay.
So that perturbation step is required. But here it is very simple that Stein coefficient exists if and only if alpha has this and this property. It's very elementary.
Okay, because he is looking for a Stein coefficient with respect to the normal.
Yes.
With respect to Gaussian. Okay.
Yeah. So it will not exist if you have a discrete distribution. So,
okay. So actually Stein coefficient, when you say Stein coefficient, it's Stein coefficient with respect to some.
Okay. I mean, so he used the word Stein coefficient. I use the word Stein coefficient. Strictly speaking, you can call his the Stein coefficient for Gaussian and this one the Stein coefficient for binomial.
Yeah, okay.
So, which is why I say that suppose you are doing some problem where you are trying to do some strong coupling to Poisson, then the natural chain is not Ehrenfest. It may be still Ehrenfest-like, I don't know. So maybe you don't need to change anything here. But the natural chain for the Poisson is not the Ehrenfest chain, but a slightly different one.
Birth, death also, right?
Huh?
Birth, you would use
Yeah,
a
birth,
death
death,
chain.
that birth, death thing. And what you would do is a modification of that.
Okay.
So that birth death chain will have a constant parameter. And if that constant is replaced by a random variable, that is what you would call Stein coefficient for Poisson.
Okay.
Okay.
Okay. I think probably
Yeah.
know.
So I guess I can stop sharing, and yeah, if people
Yes.
want, I mean, I am here. I mean, I can answer questions, but yeah.
It was very nice, Manju. Thanks.
Yeah. Thanks.
Thanks a lot.
Let's see.